Is John Thornton.
Hello and welcome. I'm John Thornton, and on behalf of Automotive Seminars and myself, welcome to our Q50 hybrid discussion. I have a few goals for our discussion today. Number one is to understand the operation of the system main relays. These are sometimes called high voltage contactors. Also, to identify the loads placed upon the high voltage battery, and to investigate a manual method to test these system main relays, and also to realize why it's important, and not just in hybrids, but in automotive diagnostics in general, to take the extra step. If we see something that has failed, to ask the question, why did this fail? What could have happened downstream that could have caused this particular failure? And you'll see what I mean as we progress. So the vehicle we are going to look at is a 2015 INFINITI Q50 hybrid HV37. When the vehicle was diagnosed last month in June, it had about 68,000 miles on it. And the concern is that the engine does not crank. Well, of course, that's the customer concern. And the engine does not crank because the hybrid system does not ready or ready up. So a little bit of background: the customer has replaced the 12-volt battery in the trunk. And I understand why the customer did that, because of the no crank situation. There is normal ignition function. So this is a push button ignition system. And if you get in the vehicle, press the button once, there's accessory, press it a second time without touching the brake pedal. We have complete ignition function, and we can talk to the manual, to modules in the vehicle. Also, the hybrid system warning lamp is on. Now, I didn't take a picture of the lamp on the cluster, but this is what it looks like. So this is an indication to us that there is an issue with the hybrid system. It should look like this. So we should have the green ready to drive, ready to propel lamp. We'll get that once the vehicle is fixed. So I'm going to start by using a Autel scan tool. And the vehicle is identified, the VIN is verified to be correct. Now, before I actually look at modules or poll modules, we should always do our homework, our research, to make sure we understand this particular application. Now, I will tell you, this is the first INFINITI Q50 hybrid that I have worked on. So this was new to me. So I had to do some homework. So there are 5 modules that are used in this particular hybrid system. So the hybrid powertrain control module kind of runs the show. It manages the hybrid system. But there's also the battery controller. There is a traction motor inverter controller. Now, a lot of hybrid transaxles have 2 motor generators inside of them. This particular Q50 has a single motor generator that they call a traction motor, but there is an inverter that is controlled by a module. So we still have an inverter. Plus we have the transmission control module and the engine control module. So when I hook up the scan tool, what I want to make sure of is that I can communicate to those modules, look at some data, and of course, pull codes. And I'll show you the relevant code in a minute or two. But I was able to talk to the engine computer. I was able to talk to the transmission computer. I was also able to talk to the inverter controller, which Autel identifies as motor control. I put the blue there in parentheses. I was also able to talk to the manager, the hybrid powertrain control module. And finally, I'm able to talk to the high voltage battery. So these 5 modules I'm able to talk to. Now I'm going to show you some data from 2 of these modules, and that'll be the hybrid powertrain control module and the battery module. Now there's not a lot of data that I'm going to show for this diagnosis because of the particular issue, but there is a lot of data available. Now, before we go any further, let's get some background on the components on the high voltage side of this particular vehicle. And like many hybrid vehicles, I'm sure you'll notice there's some similarities, but this is specific to this Q50. So let's take a look. So over here on the left side, we have the high voltage battery housing. Now, I don't want to call it just the battery, because this high voltage battery housing contains a number of components, including the high voltage lithium ion battery. It has 3 system main relays, SMRs, which I'll identify better shortly. So we have a relay 1 here, relay 2, and a pre-charge relay. And then we have some loads. are the devices that perform work for us. So one of those is a DC to DC converter, which takes the high voltage 370, 380 volts from the high voltage battery and steps it down to 14 volts for the vehicle's electrical system. Now that DC to DC converter is inside of the high voltage battery housing assembly. We also have the three-phase electric compressor. And this is the inverter symbol that INFINITI uses. So as you know from working on hybrids, that sometimes the inverter function is actually separate from the AC compressor. And if the inverter function is separate, we would have 3 cables going to the AC compressor. But when the inverter function is within the AC compressor, we have just 2 cables, as we do in this case. And our final load assembly, and I kind of combine them, that is the traction motor inverter and the motor generator or traction motor. So once again, this particular Q50 has only one motor generator. So it's called a traction motor, but it's a motor generator, and it has its own dedicated inverter. So when we talk about becoming ready, when we use that term becoming ready, it's not just ready to propel the vehicle or ready to crank the engine. When we talk about ready, we have successfully connected the high voltage battery to our loads. And our loads, again, are the DC to DC converter, the inverter and traction motor, and the AC compressor. So when we talk about being ready, we have made that physical connection. Now, in order to make that connection, we have to use these relays. So these are commonly called system main relays, SMRs. Sometimes they're identified as high voltage contactors. So while this is not a wiring diagram, it's a very effective illustration that helps us understand the job of these relays. So let me just point out a few components first, then we'll kind of walk through it. So again, this is the battery housing assembly right here, shown by the broken line. There's our battery. The 346 is the nominal voltage if you do the math and you multiply the cells, but that's just the nominal voltage. Battery voltage is typically higher than that on the scan tool. We have a junction box that contains 3 relays and a resistor. And then we have our traction motor inverter. So this is simplified, and we only are showing one of the 3 loads. The DC to DC converter and the AC compressor are not shown. Now, before I actually walk through this, there's something we got to talk about, and that is this capacitor symbol that we see right here inside of the inverter assembly for the transmission. So this is not an INFINITI illustration, but it's one that I found that allows me to talk about this and make my point. So we have here a battery. This is our high voltage battery. We have our inverter, which contains high voltage, high current switching transistors, commonly called IGBTs, insulated gate bipolar transistors. So IGBTs, and they will connect to our motor generator, our 3-phase motor. And of course, the inverter is going to serve a couple of important jobs. One, it's going to take the high voltage DC from our lithium ion battery and convert it into a high voltage AC so that we can motor. It's also going to take the 3-phase output from the generator and convert it back into high voltage DC so we can charge the high voltage battery. And that's a simple description, but that's kind of what it does. However, this is the capacitor right here that we see in this illustration. When I first learned about hybrids, I just kind of called it a capacitor. But as time has gone on and I've read more engineering papers about this, they're commonly called DC link capacitors, and they serve a very, very important job inside of this inverter assembly. And I just want to review that quickly, then we'll get back on track. So we're familiar with capacitors. We know that capacitors can smooth changes in voltage. They can temporarily store a charge and they can discharge. So they can deal with inductive spikes and surges. So why they're critical inside of an inverter is this reason. In order to go from high voltage DC into high voltage AC, we have to make sure that the input voltage to these IGBTs is fairly stable. It's stable. So the controller that's inside of the inverter is going to switch the IGBTs in the correct order to generate a sine wave. So this represents the switching function of the IGBTs in order to produce something that looks like this for the benefit of motoring, cranking the engine over, propelling the vehicle down the road. And we all know that when you have coils of wire, and if you think about a motor generator, it's a three-phase device, UVW. It's got a lot of coils of winding, and anytime you are turning coils of wire on and off very, very quickly, we're going to induce electrical noise. We're going to induce voltage. So this DC link capacitor is going to try to smooth and minimize these voltage changes both on the DC side and on the AC side. So it's very, very important. And generally speaking, it's not a single capacitor like the illustration suggests. It could be three separate capacitors. You know, they might look like a small beer can or pop can, or it might be in a housing assembly, depending on the manufacturer. But here's why it's important for us. So when it's time to connect that high voltage battery to the inverter, we have to worry about the capacitor, because as we know, in DC electronics, a discharged capacitor looks like a short temporarily. So when we connect that high voltage battery to that inverter and that discharge capacitor, there would be an inrush of current that over time could damage the capacitor and the inverter. So this is what manufacturers tend to do. So we're going to have a group of relays and we're going to control that inrush. So let's start the process on how it should work on this Q50. So again, this is our high voltage battery. That is the positive side. That is the negative side. We don't use the term ground when we talk about hybrid and high voltage. Yes, everything is connected to the chassis. It's connected to the frame, but we don't want the high voltage side connected to ground. So I'm not going to use the term ground. I'll use positive and negative. So what's going to happen is once we make the attempt to ready, the hybrid powertrain control module will send 12 volts to this coil of wire path to ground, and the contact should close. So it's all controlled by low voltage. So the contact here should close. Relay number one will close, and then we have to complete the circuit. So what will happen next, and there's a short delay, is the pre-charge relay will be commanded on. So the pre-charge relay will also receive 12 volts to the coil, permanently grounded, and this contact will close. And you'll notice that we have a resistor here. There's a typo there. I just obviously retyped. So the resistor's job here is to limit the current to a safe value so that we do not create problems in that capacitor and ultimately in the inverter assembly. So assuming conventional theory current flow. So right now we should see current should flow like this. And yes, current doesn't actually flow through a capacitor. It flows up to the capacitor, to charge the plates and whatever else is required, downstream. And then the current should come back. And that level of current might be 4, 5, 6 amps. So it's not a lot of current. We'll see that a little bit later on. But the current level is relatively low. But then very quickly, we're going to have to hand off. So once that capacitor is charged, and that might only take 400 or 500 milliseconds, once that capacitor is charged, we're going to energize main relay number 2 and de-energize the pre-charge relay. So shortly thereafter, this is what we should be left with. So this is what normal operation should be. Main relay number 1 outputs the positive side of the high voltage battery, and main relay number 2 outputs the negative side. So now we have our path of current into and out of the inverter. So the pre-charge relay and that resistor are only used for a short period of time, maybe 600-700 milliseconds total before we are ready to go. So that's what normal looks like. That's our expectation. So now it's time to do some testing. So I have the scan tool connected, and I am talking to the hybrid powertrain control module, which controls these relays. And I want to see what's happening with the relays. Now, unfortunately, I can't really take a movie and show graphs because the Autel does not support that for on-off PIDs. But I did take a movie nonetheless. So right now, I have the ignition on. I'm not trying to make a ready attempt, and I'm looking at my relays. So here's the pre-charge relay. Here's positive, that's relay number 1, and negative, relay number 2. As expected, ignition on only, all 3 are commanded off. So that's expected. So now I'm going to make a ready attempt. I'm going to depress the brake pedal and push the power button, and I'm going to record it. So you can kind of see that I'm going to play this. I'm playing this back. You can see I got a frame count and I got a time count. So initially, all 3 are commanded off. So think about what our expectation is. We expect the positive relay number 1 to come on first. And that's what happens. And you can see my frame start to increment down here. So that's good. That's normal. So then we expect the pre-charge relay to come on second. And it does. So that's good. So that means at this moment in time, we should be supplying voltage to the inverter, and of course the AC compressor and the DC to DC converter. So there should be voltage being applied right now. The resistor is limiting the current, but we should be applying voltage. And then I expect a handoff. I expect the negative relay to come on. I expect all 3 to come on, and then I expect the pre-charge to turn off. But unfortunately, that's not what happens. So here's what happens next. For some reason, the pre-charge relay turned off. So it turned off, main relay positive side stayed on, then it turns off and the pre-charge comes back on. Very odd, but this was completely repeatable. Every time I made a ready attempt, this is what I saw. The main relay came on first, pre-charge came on second, main relay turned off, and then pre-charge came back on, and then it turned off as well. This was very consistent. So clearly we're not energizing the negative relay. So therefore we can't ready. And every time this occurs, we have a code. Now this vehicle, and specifically the modules that relate to the hybrid system, had a number of codes. And of course, one of our challenges is to make sure we understand what codes are relevant and what codes really are not relevant to the diagnosis. So I'm not going to talk about those other codes, but I will assure you that this is the code that comes back every time after I clear a code and make a ready attempt. So this P0A95 is the code, and it's called high voltage fuse. We'll investigate that in just a moment or two. So there's one other module I want to talk to, and that's the high voltage battery. And I'm interested in seeing, did voltage head out to the inverter? So I just have 3 data PIDs up here. So this is high voltage battery. So this is what's, a little bit of a charge in that battery. So it's about 380 volts. And I'm looking at battery current. You'll see a little bit later on, there is a current probe, a current sensor that's used to measure output on the positive side of the high voltage battery, and inverter voltage. Now the scan tool shows me 2. For practical purposes, I think we could just say that's basically 0. So this is what I see when I turn the ignition on without making a ready attempt. So it looks pretty good. However, when I make the ready attempt, nothing changes. This doesn't come down, it doesn't drop, doesn't lower, the current doesn't change, and the voltage doesn't change. And this is bothersome because briefly, and it's brief, that for that moment in time here, both the positive relay and the pre-charge, which is on the negative side, were on for a short period of time. It was brief. It was brief. So my expectation is if both of those are on, and think about where we're coming from, if both of those are on, voltage should be made available to the inverter. But it wasn't. So that was kind of bothersome. And I wasn't sure if that's because there's an issue, or was the refresh rate on the scan tool, not, a little too slow, and maybe it didn't catch it because it was happening pretty quick. So, I wasn't 100% sure on which it was at this point, to be quite honest. So if I were to pause and just say what I know right now is that, well, the hybrid system doesn't ready. The negative system main relay is not being commanded on. It's not being commanded on, and we don't see inverter voltage and we don't see inverter current. So it kind of looks like that maybe we're not actually switching the voltage out from the high voltage battery, but we need to confirm that another way. I'm going to add this, though it's not critical for this particular diagnosis. You know, when you're dealing with a no crank on a hybrid because it doesn't ready, you know, the battery is not really being stressed. So, you know, so we're not loading the battery. But if this complaint had been the engine cranks but does not start, then we really have to pay close attention to battery voltage and battery state of charge. So that's not the complaint on this vehicle, but I kind of out of habit, I always look at battery voltage and state of charge just to see what we have. So it looked good on this particular vehicle. So let's focus a little bit on the code. So it's a P0A95, and I'm going to the INFINITI website for all the service information. So when I looked it up, just like the scan tool says, high voltage fuse. Now, I'll tell you what I thought. I thought that initially what this meant was the fuse that's in the service plug. And the service plug is the plug we remove, you know, for safety, for working around hybrids. Because I know there's fuses in those plugs, maybe not every one, but many do have fuses. And I thought initially, well, maybe they mean that fuse is blown. But then I thought to myself, you know what, that can't be. That can't be true, because if the fuse was blown or if the service plug was removed, we would not see full high voltage on the scan tool. So if you recall from just a couple of minutes ago, we saw about 380 volts at the battery. I did this intentionally, not so much from an educational viewpoint, but just to confirm my suspicion that, well, if I pull that service plug out, my battery voltage should be reduced, and it is about 150 volts. So it can't be this fuse. So obviously we have to, you know, move forward. So in service information, they give us the detecting condition. And I'd just like to read this sentence to you. When the hybrid powertrain control module detects lithium ion battery current is more than a -3 amps and traction motor inverter input voltage is less than 25 volts for 450 milliseconds during pre-charge. Well, this is occurring during pre-charge because the negative relay number 2 never is commanded on. So that's correct. This is a tricky description, in my opinion. I understand, I'm sure you understand what less than 25 volts means. And we're less than 25 volts. The scanner showed 2. I understand that, but I'm not 100% sure I understand the more than a -3 amps. Now, many times when hybrid batteries are discharging, for example, cranking an engine over, propelling the vehicle down the road, a manufacturer may assign that as being negative. So negative current would suggest that the battery is discharging, and positive current would suggest the battery is being charged. And I understand that. But here, when they say more than 3 amps, maybe they're saying, yeah, the battery is being discharged. Or maybe if I think about it from a mathematical viewpoint, well, a +3 is more than a -3. 0 is more than a -3 from a math viewpoint. So I'm not exactly sure which way they want me to take this. So I'm not going to lose too much sleep over it. But I do know that what less than 25 volts means. So, and we have that condition. So I think it describes it reasonably well. So then they go on to say, these are some possible causes. So I've made some modifications here, but first one, they say, you know, harness and connectors. And please notice what they say then in parentheses. High voltage direct current is open or shorted. Okay, well, if you have an open, obviously there's going to be no current flow. And depending where the open is, there may be no voltage available to the inverter. Now, if you have a short, generally shorts blow fuses, and if fuses blow, then we have an open anyway. So getting back to the code, it's a high voltage fuse code. So, okay, maybe that makes sense. Then they say, well, some possibilities include, could be our 3 relays. That's a possible. Could be our 3 loads, the motor inverter and motor generator inside the trans. That's one load, the DC to DC converter, and our AC compressor. So it could be one of the loads. They also say it could be the battery controller, and maybe that's an input from the controller to the hybrid powertrain control module that makes the hybrid powertrain control module believes there's a problem. And then they say high voltage fuse, which I still wasn't that clear on. However, I learned, and you'll see this coming up, that there's a device, this battery junction box that houses the 3 system main relays, also houses 3 fuses. Now, initially, I didn't know that. And I had no idea, what these fuses would even be used for, but we'll investigate that. So now it's time to start our testing. And we're going to do our work primarily in the trunk. The 12-volt battery is over there on your left. A battery charger was connected at all times. So as we did our testing here. Now, before we dig in, I want to make the safety comment here. And this is very, very important. So when you are preparing to work on the high voltage system, and we're going to be working on the hybrid high voltage system, we have to observe safety. So generally there's 3 steps. Number 1, we power down ignition. So make sure the ignition is turned off, whether it be a push button or a blade key. Number 2, we remove the service plug. So you can see my white arrow here, service plug is out. And then number 3, we wait about 10 minutes for that DC link capacitor to discharge. And if you want to take it a step further, use your approved multimeter and verify there is no voltage coming out from the junction box. And I'll show you how that was done. So this is our high voltage battery assembly. I'm going to give you a little bit of background before I actually do any tests here. So this is the battery out of the vehicle, obviously on the ground. And that was done as part of the repair. So these pictures were taken at a later time. So obviously, to give you some reference, that's where the service plug would go, right there. And let me show you an INFINITI picture here first. So inside of this battery housing assembly, of course, is the high voltage battery. But there are some additional components. So the DC to DC converter is over here on the left side. So that's over here. The battery controller is also inside of our battery housing assembly. And there's the junction box. Those are the relays. I have better pictures coming up. So those are the relays. And that's actually right about here. It's behind this plastic connector housing. So it's right behind that. This is the connector for the air conditioning compressor. So you can see it's disconnected in this picture. That's the female side. And the female side goes underneath the vehicle to the engine compartment for the compressor. And these are the 2 inverter orange cables right there. They, along with the AC cables, go underneath the vehicle to the engine compartment. So a little bit better picture here. So again, here's the AC connector. This is a plastic housing that connects the output of the junction box that houses the relays directly to the 2 orange cables that go to the inverter. So this cable you see here and that cable you see here are connected at the top here. So that stud, that's the negative side, and that's the positive side. Those are marked. You can't tell in this picture, but they're actually marked on this black plastic housing. That's negative, that's positive. If I go back here, so those are the cables you see right there that are heading to the inverter directly. So we can access those studs. There's some sheet metal that has to be removed. There's a white plastic connector that we can clip off. But again, using care, being safe, having the right meter or scope adapter, we can hop on these studs and we can measure the voltage ourselves. So now that we kind of have a feel for the layout, and I have more pictures to come, we're going to do some testing. So my goal right now is to test the output of the hybrid powertrain control module and see how it's energizing these relays. Now, I want you to know that I'm not doing this because I don't trust the scan data. I'm sure the scan data is spot on. I have an ulterior motive that you will see in a moment. So here's our hybrid powertrain control module, and we already know it provides 12 volts on each of these 3 circuits to energize those relays. Now, this is an illustration. It's not a wiring diagram. So I need to find the wiring diagram to get on the right wires. And that's a challenge. So again, I'm on the INFINITI website, and normally speaking, I use Nissan INFINITI wiring diagrams on their website frequently. I'm somewhat comfortable with them. I like them, but this was a challenge. Let me explain what we're looking at. Down here at the bottom where it's green, this is again, it's a small piece because I wanted to make this as big as possible. This is the hybrid powertrain control module. This is a small piece of it. And I know 3 of these wires are the wires that I want. This is the battery assembly here. And there's the DC to DC converter. There's that junction box. It houses the relays. There's part of the battery controller. And there's some other connectors coming into it. So I'm thinking to myself, okay, how do I figure out those three wires? Well, I'm going to kind of get ahead of myself right now. If you'll notice, I have three pins circled down here. So number 3, 15, and 34. Those are these three wires. Now, when you look at this, if you trace this in, this actually goes to the junction box. So you can say, John, well, that wasn't too tough. However, these two over here do not. So I don't think INFINITI is intentionally misleading us. I don't really think they feel it's that important to show the detail here. So the way you do this is, and it's very easy to do on their website. You find the component that you're interested. I'm interested in the hybrid powertrain control module, and then you pull up the connector list, so you can see B14, B15, etc. And then you look at the circuits within the connector list. So B14 is this 40 cavity connector that you see down here, 2 rows of 20. And then when I open this up, I can look at individual circuits, and I did this through a cut and paste. So pin 3 is a white wire, that's pre-charge. So that's the pre-charge relay control. Pin 15 is a gray wire, that's the negative main relay number 2. And pin 34, brown wire, that's positive relay or main relay number 1. So now I have the pin locations and the colors. I just have to find the hybrid powertrain control module. And it turns out it's in a great spot. So this is the battery. Everything, of course, this is all done. Everything was still in the vehicle when the testing was done. And it's right here. So you really couldn't ask for an easier access. So there's the connector right there. That's our 40 cavity connector. So knowing the wires, knowing the cavities, carefully going to back probe. So keep in mind, this is low voltage DC, but it's never a bad idea, again, to observe safety. When I was doing this, I had the ignition off, service plug out. So again, those are habits you create or have over time. So it's never a bad idea, keep things, be safe, and then put things back together when you're ready to test. So now I'm ready to test. So I ready up, and this is what I see. So first of all, red is the negative relay number 2, and you can see absolutely no activity. Exactly what the scan tool showed us. Green is the positive main relay. So it got turned on, it went up to, again, there's a charger on here, so maybe 13 volts, and shut off. And then the pre-charge. So let me zoom in here a little bit. So positive came on first. They staggered the pre-charge, and that's done for diagnostic purposes as well. So the pre-charge was on, then it got turned off. Now, interestingly, if you'll note where my cursors are, for that 460 milliseconds, both the positive and the pre-charge, which is on the negative lay, are turned on, which means for 460 milliseconds, there should have been voltage at the inverter, or should have been current flow to the inverter. Now, we never saw that. And again, I was wondering, is it possible that it was too fast for the scan tool? So I'm still not 100% sure on that, but 460 milliseconds, that's almost a half a second. I would have thought the scan tool would have caught it. So maybe it's not a scan tool issue. Maybe it's just not happening. But this is one of the benefits of actually looking at the controls. But again, I have another reason here. So one of the other things that was done, since I had already identified the wires, I had pinned the wires. Once I made those checks, I did some quick resistance checks. Now, I will tell you this is not necessary, but it's good for the database. I hope one day to have another Q50 hybrid with an issue, and I'll have some data that I created that might be helpful to me. So both main relays, the coil windings were about 28 ohms. The pre-charge was much higher at 108. And I've seen similar type of values with other hybrids. So, that seemed reasonable to me. Also, if you look at my bottom bullet here, I manually energized the relays with this connector disconnected. So I just took 12 volts, the battery's in the trunk. I just took 12 volts, and one at a time, I energized them, and I heard them click. So granted, it's not a great test, but it's a test we all use, and at least tells me, I can hear the relays and they are functional. So I believe the the hybrid powertrain control module is capable, the circuitry is good, and the relays are capable of closing. That's what I know here. So I'm going to do one more thing here. I'm going to connect a voltmeter to those studs in that plastic junction housing, and I'm going to make a ready attempt. Now, I did not take a photograph of this. I got a good post repair, but I did not actually do this one. So this is just kind of a cut and paste to show you what I was doing here. So I do have a Fluke 1587. It doesn't look like the one in the picture, but I took the positive lead and I went to the positive stud. There's again sheet metal and a connector was removed. It's marked, and I took my black lead and I went to the negative stud. And I made a ready attempt. So we now know for about 460 milliseconds, there should be voltage there. And there was no voltage. It was 0 volts. So no output at all. So let's think about what we know. The hybrid powertrain control module energizes main relay number 1. It energizes the pre-charge relay. My meter is right here. So those my circles, the red and green, positive, negative, they represent the studs. That's where I'm. There's nothing there. So it looks like the problem is internal to the battery housing assembly, but I need more information. I need to figure out, is it the positive relay? Is it the pre-charge relay circuit? So what could you do? I mean, if you take what we do every day when it comes to circuit issues, what could I do here to kind of get more in-depth information regarding the diagnosis? Exactly. I'm going to take manual control. I'm already connected. So what I'm going to do is I'm going to energize the relays myself. So again, everything was connected. I do observe safety. So I took a jumper wire and I applied. Peter, we good?
Hello, John. It is actually lagging. I was just about to stop you.
Okay. I mean, can you hear me okay? I mean, everybody see me, hear me?
Wave your hands in the air if you don't mind. Okay, yep, it just caught up.
Okay. All right, so.
Sorry about that. It was going on for about 45 seconds and I was trying to, it should be good now.
Okay, just jump in if there's a problem. So what I'm going to do here is manually energize the relays. So I'm going to energize the positive relay first. So I'm just going to put 12 volts here and I'm going to energize that relay. And with that jumper wire connected, I'm now going to energize relay number 2, the negative relay. So I'm going to put 12 volts here. Now you're saying to yourself, well, John, is that a good idea? Because you already talked about this DC link capacitor, and you talked about that if the capacitor is discharged, there would be a surge current. I recognize that. I understand that. I am not going to do this multiple times. My goal is never to cause a component to fail, but I want to make a decision on what I should do next here. So I'm going to do this quickly. And then, once you do it the first time, assuming current did flow, then I could do it a couple more times once the capacitor is charged. So yes, I realize there's a risk, but again, I don't think 1 or 2 attempts is going to do any damage here. So I energize both relays and I see on my meter about 379 volts, remarkably close to what the scan tool showed. So I have the ability to have voltage come out by energizing those 2 relays. So I hope, again, that interruption wasn't too much of an issue here. So I was right here with the meter. And relay 1 was energized, relay 2 was energized. It's fine. We have what we need. So I believe the problem is that we have an open on the pre-charge side. So it could be the conductor, it could be the contacts of the relay could be bad, or it could be that resistor. I'm not really sure which it is, but I do hear the contacts close, when I hotwire it. So I'm kind of leaning towards the resistor, but frankly, I don't know. But I do know with a high level of confidence, the problem is on the pre-charged circuit. So that high voltage battery junction box needs to be replaced, and it can be replaced separately from the high voltage battery. So you don't have to replace the battery assembly. You can buy the box from INFINITI. However, and this is what we have to think about, what caused this problem? again, I've been fortunate over the years. I do work on a fair amount of hybrids, primarily Toyotas, Fords, a little bit of GM, a little bit of Hyundai Kia. And I don't normally see a lot of relay failures. I've seen some due to water intrusion, flooding, that type of thing. So I wonder what caused this problem. Is it too much current flow? And I'm thinking about this code, the fuse code. Is it heat? What created this issue? So we know that the junction box switches the high voltage battery to the loads, the DC to DC converter, the AC compressor, and the inverters and traction motor generator. So I'm concerned that if we just replace the junction box, that might not be the issue. So I do a little bit more research on this junction box, and you can see in this picture from INFINITI that they show the relays, and then you can see there's some fuses there. So I go back to the INFINITI website and I'm digging through, information, and I come across this diagram, and it's much bigger than what you see here. Again, I cut and paste it to make this fit, but this is what I would call the key to a successful diagnosis. This was the key so that I didn't miss something. So it's a little busy. I'm going to take it through in a few steps, but let me show you what we're looking at here. So up top here, you can kind of tell those are the battery cells right there. And again, let me just outline, this is the battery assembly. So let me just outline the battery assembly for you. So this is the battery assembly. So we're just looking at a piece. So we got the battery, of course. We have some temperature sensors. The DC to DC converter, as you know, is inside the battery housing. It's kind of on the left side as you're looking in the trunk. Here's the junction box in yellow. And there's the hybrid powertrain control module, which is above the battery. And then we have outputs, traction motor, motor generator, inverter, and compressor, AC compressor. And again, there's a DC to DC converter. So what I want to do now is I want to look at the paths, how the battery current is routed via these relays. And I'm going to do main relay number 1 first, which is the positive side. So I'm using red here. So this is the positive leg of the high voltage battery. I'm going to follow it out. So I'm within the housing, and it comes into the junction box. And if I actually had the junction box in front of me, it comes in at the top. So it comes into the junction box. It goes through a current probe. That's where we got the current measurement from. We're going to assume that relay, our contacts are closed. It comes out, and then we have a junction. We have a split. We know there's 3 loads. So this is going to the traction motor inverter under the hood. Another leg goes to the DC to DC converter. Okay, positive. And to the AC compressor. You saw that, right? There's a 30 amp fuse. So that compressor's got a 30 amp fuse. So now we know a little bit more. So now let's do the pre-charge. Pre-charge and relay 2 are on the negative side of the high voltage battery. So I'm going to trace the negative. Relay 2 is open, so we don't go there. Relay pre-charge is closed. There's the resistor. And again, we have a junction. So in parallel, there's our traction motor inverter, one of the orange cables. This is heading to the DC to DC converter, negative leg, but we saw it. There's a 15 amp fuse. So the DC to DC converter is protected by this 15 amp fuse. And finally, on the negative leg, the AC compressor has another 30 amp fuse. And if I look at just relay number 2, which of course is the negative side, it's going to be very similar. Inverter, no fuse shown. DC to DC converter, 15 amp fuse, and AC compressor. So this illustration was extremely useful. So now we know that this AC compressor is protected by 2 30 amp fuses, and the DC to DC converter is protected by a single 15 amp fuse. And there's no inverter fuse within the junction box. So I learned that. So this is a picture of the old junction box, obviously removed from the battery housing assembly, just kind of showing you, a layout. So these are the 2 system main relays. There's the pre-charge, and these are our 3 fuses. And these are the glass sand-filled fuses that are used with hybrids or high voltage in general. So you can't really tell by looking if the fuses are good or bad. You have to measure. So it turns out we can do that. In the vehicle, we can actually check the resistance of the fuses. It's a little tight, but it's doable. So once again, observe safety, make sure ignition's off, service plug is removed, wait 10 minutes and measure voltage. So you can see this plastic housing, which connects the output of the junction box to the inverter, has been pulled forward. And I'm going to get my camera in there, and you can see there's the junction box. You can see one fuse. That's a second. I got a better view here. So you can see the fuses. So you can bet. So if I can take a picture of it, we can measure it. And I use the term we, but not just all of us. But when I was at this shop, the shop owner, Mike, a mutual friend, Steve, who teaches hybrids at a junior college, we were there. The three of us were together doing this together. It was enjoyable, educational, diagnostic. So here's what we learned. So the 15 amp fuse for the DC to DC converter was fine. It had continuity, but both 30 amp fuses for the AC compressor were open. They were both open. Now, just to bring you back here, in case there's a question, I'm not able to handle questions, but if I think about questions, in a class environment, we were measuring the voltage with the meter at those studs. The studs are here. That would be the stud. That would be the stud. The 30 amp fuses do not impact the path to the inverter. So even though those 30 amp fuses were blown, there will be no output to the compressor, but it doesn't prevent voltage from the inverter. I mean, especially when I use the jumpers, to bypass it. So don't think that 30 amps are in series with everything. They're strictly for the compressor. So, so not a question is, okay, so we went a little further. We asked ourselves, why did this pre-charge circuit fail? Well, now we have two blown 30 amp fuses. So conceivably, this short that blew those fuses probably was so great that maybe before the fuses blew, or at about the same time, too much current flowed through the pre-charge, and maybe that resistor was a weak link. Maybe, I don't know for sure, and it blew. So we have a common issue for everything. So of course, when you ask yourself what causes AC fuses to blow, well, something to do with the AC circuit. So back to the vehicle. So this is that AC connector that comes from the junction box. It's now currently disconnected, and the connector going under the vehicle, ultimately to the compressor, is being tested. And you can see my ohm meter. Yeah, it's 1.2 ohms. So I'll give you an up close look. So we are measuring right here. You can see exactly where the meter leads are, and the meter showing a 1 ohm. So that's a short. Now, I don't have a spec on what good is, but I expect, thousands and thousands or 100,000s of ohms, a lot of resistance to an inverter, because that's really where we're going. So, but before we can jump the gun here, it's possible that this issue could be maybe the cabling is shorted. Maybe it's not the compressor. So this picture, you can see my note here, that's with the compressor connected. And then we disconnected the compressor. So we just went under the hood, disconnect the compressor, fairly easy. And you can see the meter goes OL. So this tells us it's not the cabling, it is indeed the compressor. So to fix this vehicle, we need a junction box. Why do we need a junction box? Well, there's a open in the pre-charge circuit, and there's two blown 30 amp fuses, and the vehicle needs an air conditioning compressor and all the associated work that's required when you put a compressor in a vehicle on a modern day. So can you imagine that if we had just diagnosed the junction box, if we had said, slam dunk, the junction box is bad, it needs a junction box, and we didn't get to the compressor, what would have happened? New junction box, and as soon as you make a ready attempt, if it would even ready, we'd be back to the same boat. So this is why it's important to kind of ask the question, what caused this issue? Why? Is there something downstream? And that's true with automotive in general, but certainly when you're talking about a high voltage side on a hybrid, we have to think about that. So the vehicle gets repaired. The shop installs a junction box. They remove the battery to do that. I found out recently from talking to a gentleman that it can be done in the vehicle. I did not know that, but it was done outside the vehicle. And the shop, of course, did the air conditioning work. So the shop owner was kind enough to send me this picture. So here's a brand new compressor on the bench, and he's doing an ohm check. So you can see it's about 678,000 ohms, or about 0.7 meg. Pretty far cry from 1 ohm. So we have about 10 minutes left in our discussion. So I'm going to show you some post repair data. So the shop was kind enough to allow me to come back before they delivered the vehicle so I could get some good data on the vehicle. So let's take a look at some known good. So the vehicle's fixed. Now it readies. It's ready to go back to the consumer. So going back to the hybrid powertrain control module and monitoring our 3 relay SMR controls, this is what normal looks like. So here's the positive. I'll open it up a little bit here. So here's the positive. It turns on first. A moment later, I'll give you a sense of the time here. The pre-charge comes on. So right now we should be charging the capacitor, the discharge capacitor in the inverter assembly. And then we start the handover. So now you can see, even though the pre-charge is still on, the negative turns on. So that's great news there. So the negative turns on. And then right about there, you can see the pre-charge turns off and we are officially ready. We are ready to propel. We are ready to start the vehicle. And you can see how the voltage stepped up a little bit as the DC to DC converter went online. So if you look at the time here, so the positive SMR where I have my scope trigger, that's at second 0. Right here, that's just under 600 milliseconds. So within a 600 millisecond window, we readied. So that's what normal looks like. This is what good is. And again, there's staggering here of the relays for some diagnostic purposes as well. Let me show you a couple other things before the time goes away. So I also wanted to measure inverter voltage, but I wanted to tie it into the control of the relays. And again, the scan tool does all this. I mean, I had post-repair scan data, but I wanted to kind of tie it in with the scope. So I'm going to use a differential probe at 100 to 1, so that, of course, I'm going to protect my scope module, my Pico box. So I am going to access, again, notice the service plug, or the lack of service plug. So this is all back together. So I pulled a metal shield off, and there's this little plastic cover here, and these are the studs. So I'm going to pull this back. I'm going to hook up my Pico differential probe. It's an older one, and I'm going to take its alligator clips, and I'm going to put them right at those studs. So earlier I told you I didn't have a good picture for the meter, but this gives you a good idea. So that's the negative stud there, and the positive one, I just kind of snuck it in behind the plastic box. So I'm right on the inverter output. Again, this was all done using, safety first. It was all, system was powered on. So then everything gets reconnected and I ready up. So gold is the high voltage. So you can see, I've got a few zooms here to make it look a little bit better. So that's 0. And right there, it's about 378 volts. Very close to what the meter showed when I energized it, with the jumpers, and what we initially saw with the scan tool. So let me make the voltage a little bit bigger and reorganize my screen. So you can see, the main relay, positive turns on first, then pre-charge with the resistor turns on, and notice the ramping. Notice how the voltage ramps. Let me give you a better view of that. And again, getting back to DC electronics, we have been taught that when you apply voltage to a discharge capacitor, we have been taught that current leads and voltage lags. So current leads, voltage lags. Why does the current lead? Because a discharge capacitor for a moment in time looks like a short to a DC power supply, a high voltage battery. And you can use time constants to figure out how long it takes to reach the voltage. Not necessary for what we're doing, but you can definitely see that the voltage built until it hit that 378.80 volts. And I just made a measurement. I could be off a little bit here, but it looks like it took about 230 milliseconds in order to charge the capacitor. We can take it a step further, and we got 5 minutes. We got plenty of time. So now I'm going to take a high amp current probe. And again, this is not necessary because this data is available from the scan tool, but it's an interesting exercise when you want to look at everything on a scope and you want to make the comparisons. So I've taken a high amp current probe, a 2000 amp current probe, and I've clamped it around one of the inverter cables. So again, there's these three cables go underneath the vehicle. So that's an inverter cable. That's an inverter cable. That's really a sheath, a covering, if you will, because both AC cables are inside of that. So make sure you get on the right one. So I'm on an inverter cable. And now again, I'm ready. So the relays are removed. We're just looking at high voltage battery and inverter current. So this is current to the inverter, not the AC compressor and not the DC to DC converter, just the inverter for the transmission. And you can see my note here. I readied up and the engine started. So, the engine cranked, started, and ran. I'm going to zoom in a little bit. So our current is hitting about 40 amps. And that's the current, that's the initial level of current, to start to crank the engine over, cranking, engine starts. And now you can see the current goes below zero, relatively speaking, and then we start to charge that high voltage battery. Notice over here. Now that was for cranking. So that's the inverter and the traction motor performing work. What do you think that current pulse is? Let's take a closer look. So I've zoomed in, I've changed my scales, and you'll see my note here. All I did was ready, and the engine did not start. I wanted to make sure I got to the point where I could ready without the engine starting. So it just readied up. And you can see, of course, the voltage as we go through pre-charge. We talked about that. Look at the current. That's the surge current that's limited by that resistor. So once again, when you apply a DC power supply to a discharge capacitor, current leads, voltage lags. So you can see the current immediately jumps to 6 amps. That's what it's controlled to. And as the current starts to taper, you can see the voltage is building. So right here, and that's kind of what you saw over here. That's what happens when we initially ready up. And I did some brake torques just to look at the current change. And you can see I was hitting levels of about 50 amps as I was loading the vehicle in the bay. So we are about a minute shy, which is okay. Got it in an hour. So when I started this discussion, my goals were, there were a handful, but I wanted to talk about how the system main relays operate, why we have a pre-charge relay, why we have that resistor, the importance of that DC link capacitor, how that all plays together. So I hope the case study helped with that understanding. We also need to identify the loads. And in most hybrid systems, the loads are similar. You're going to have an inverter for your motor generator or motor generators. And on a lot of course, late model hybrids, we have an air conditioning compressor that may have an inverter inside of it, or it might be external. And it's never a bad idea to have methods to check things manually, whether it be using jumper wires, a scope, a meter. Not to say that the scan tool doesn't get the job done, but sometimes you need a little reinforcement, or you want to come up with some tests that can help you navigate. And also, as you saw here, if we had stopped the diagnosis with the junction box, we would have been at it again. So this is why it's important to always kind of ask that question, why? What caused this to fail? And yes, of course, there's always going to be times a component fails for no other reason than the component failed itself. But here, of course, that air conditioning compressor shorting, for whatever reason, why ever it did that, it took out those 230 amp fuses and it took out the pre-charge circuit. So there was quite a bit here to kind of follow through. So it is 1 o'clock. Thank you very, very much for giving up 1 hour of your time. Hopefully this was a benefit. Look forward to seeing you again. Thanks everyone. Pete, Tim, thank you. Have a good rest of the day.
Great job, John, as always.
Okay.
All right. Thank you everyone for joining us. And if you like this class, please visit our website to find more information on our upcoming training. Thank you.